Today, I just want to give you a quick review over the gas laws. We covered this pretty well in Chem 1, but just a few reminders. First of all, remember we have Dalton's Law of partial pressures. Dalton's Law of partial pressures simply says that if you have a container and it has different gases in it, that the entire pressure of the whole container is going to be equal to each of the individual gases' partial pressures added together. So if you have oxygen and hydrogen and helium and they all have 1 atmosphere of pressure each, then your total pressure in the container would simply be 3 atmospheres. Also remember that you can convert back and forth between pressure units. These are the common pressure units. I would say kilopascals is more common in physics, but atmospheres, millimeters of mercury, torr, we see those all the time in chemistry, so we need to know all of them. We can set up, remember, conversion factors between any two of these. So you can set up the fact that 1 atmosphere is equivalent to 760 millimeters of mercury, et cetera, et cetera, et cetera, and use those as conversion factors. So just a little picture of a barometer. Occasionally you'll see on the AP test they'll show you a picture of different types of barometers, and they simply work on the fact, in this case, mercury in a vacuum tube, and the higher the air pressure is, as it shows here, the more it pushes down on the mercury and pushes it up into that tube, and they simply measure that. Now this one's measured in inches of mercury, which is kind of common in the US, but we're never going to see that in any of our chemistry questions, or at least I've never seen it so far. Now as far as the general or combined gas law, this should be familiar also. P1V1 over T1 equals P2V2 over T2. Doesn't really matter for this equation what pressure is in, as long as it's the same on both sides. The units will end up canceling anyway. Same way with the volume, but temperature, this is the one that's going to just kick you in the teeth if you don't remember that temperature has to be measured in kelvins. Remember, to get a Kelvin temperature, you have to simply take the degrees Celsius and add 273 to it to get that value. But it's got to be in kelvins. You can't do any of the gas laws in any other temperature except for kelvins, absolute temperature. So from this law we can get other laws. Charles' law, all we do with the combined gas law, remember, is just drop out the parts that we don't use. Charles' law, Charlie Brown is on TV, if you remember. Temperature and volume involved. They are directly proportional. When one goes up, the other goes down. And we can simply take volume and temperature out of the combined gas law and say that V1 over T1 equals V2 over T2 for Charles' law. Boyles' law involves only pressure and volume, and students long ago came up with the fact that Boyles have press and volume, which I think is kind of gross, but the gross one is the only one that's inversely proportional. So it kind of works to help us remember that when pressure goes up in the system, the volume goes down, and vice versa. So Boyle's law, since it only deals with pressure and volume, we pull just those two from our equation above, just the pressure and volume part, and we get P1 V1 equals P2 V2, dropping out the temperature from that equation. Finally, Guy-Lussac's law, guys like power tools. I'm saying girls like power tools also, but it doesn't work with our little analogy here. So guys like power tools, temperature and pressure, they're also directly related. The gross one is the only one that's inversely related. And when temperature goes up, pressure goes up, vice versa. So Guy-Lussac's law, pulling out only temperature and pressure, we get P1 over T1 equals P2 over T2. So those are our individual equations for those different laws. And we can use those anytime we're changing conditions. Now the ideal gas law is meant to be used to deal with moles. And for the ideal gas law, it does matter what units you have everything in. If you remember, obviously kelvins has to be true. This is what I call an R-driven equation. An R-driven equation, R is a constant, and the constant most often used for the gas laws is this one, 0.0821 liter atmospheres per mole Kelvin. I always say lattimolks. It sticks in people's heads way longer. 0.0821 lattimolks, liter atmospheres per mole Kelvin. So notice that volume then must match. We've got to have volume in liters. We've got to have pressure in atmospheres. It didn't matter in the combined or general gas law, but it definitely matters in this one. Must have those units be consistent with R. So one of the forms that we often use for this one, if we remember that the number of moles is the mass of the substance divided by its molar mass. So if N is mass over molar mass, then we can write simply, remembering that those have abbreviations of small m over kind of a big cursive M for molar mass, we can rewrite this equation to a form that's often more useful to us because occasionally it'll deal with moles, but most often it's talking about the mass of substance. I guess just to up that difficulty level just a little bit. So we've got mass over molar mass times RT. And most like to write it as PV equals MRT over molar mass. It just works a little bit better in our heads when we start trying to rearrange those equations. Now, density of gases, you can derive this equation from the ideal gas law, but I just would rather just memorize this equation. It's much quicker. That cursive M is molar mass, as we see over here. And the density is going to be in grams per liter when we get done. I've always remembered this as I'm dense at night, right? I'm a morning person. So that's how I've always memorized that equation. You can find another way to memorize it if you want to, but that's the way I've always remembered that equation. It's just a little bit of a help. It won't be in the AP test. It won't be one of those equations that they give you, but it's a very helpful equation to memorize. Avogadro's law. The same number of moles or molecules of any gas occupies the same volume at the same temperature and pressure. Occasionally, you'll see the combined gas law written like this. P1V1 over T1N1 equals P2V2 over T2N2. You'll see them put that number of moles into the equation and use it that way. I don't like putting it in there all the time because it makes it sound like if you change the volume, you can change the moles. But you can definitely, by changing the number of moles, change the pressure, volume, and temperature. So it is useful once in a while. Nice thing to remember that it's still proportional like that. But like I said, I don't normally write it that way. Kinetic energy, KE, the kinetic energy is 1/2 the mass times the velocity squared. Kinetic energy is in joules. Important in some of our applications to remember that a joule is a kilogram meter squared per second squared. We'll see that come up in our next set of notes. Now, here's the kicker. Mass is in kilograms because of that joule value for our energy. And that's the thing that people often forget to do, is to make sure that that mass is in kilograms. And of course, velocity is in meters squared. Not doing a sample problem, it's a simple equation, but it's one that you need to be aware of. Now, here's the big thing, and I need to put like 52 circles around this. Why I chose 52, I don't know, but at the same temperature, the kinetic energy of all gases is the same. I can't begin to tell you how many questions on the AP test this statement has affected. When they ask you all this stuff and you don't know what they're talking about because you've forgotten that if it is at the same temperature, the kinetic energy of all gases is the same. The way that they change, obviously, is in their mass. They don't all have the same mass, and because they don't all have the same mass, they don't all have the same velocity either. Our bigger molecules, bigger substances have have lower velocities. Our smaller ones have the higher velocities, and that's what makes them equal out to have the same kinetic energy. So keep that in mind. Just a couple of graphs real quick. Speed of gas particles, even the same temperature, are not the same. Notice as you get more or get higher and higher in temperature here, yes, you get the majority of the molecules moving faster and faster. We've got number of molecules here on the side, speed at the bottom. Um, but notice in any given container, not we're talking about the average speed when we talk about how fast something's moving. We're not talking about the speed of every molecule. There may be molecules at 2,000 degrees that are virtually not moving at all down here. Or we might have something at 0 degrees and you've got a couple of rogue molecules up here going really fast. So keep that in mind, and this Boltzmann distribution curve shows that it simply means the majority of the molecules are going to move faster and faster um, as the temperature increases. So that's what a Boltzmann distribution curve shows us. And finally here at the bottom, it's just giving us just an example of some average, remember, speeds at 25 degrees Celsius for our different sizes of molecules. Temperature's the same here, but you'll notice that as we get the molecular weight increasing, our speed keeps going down and down. So those are just some conceptual ideas that you need to be keep in mind when you're answering some of those AP questions.